Deep within southern Jordan's hyper-arid desert, precipitation is minimal and evaporation rates exceed recharge capacity. These rose-red sandstone massifs exhibit high porosity, yet lack permanent surface water sources. Here lies Petra, an urban system carved directly into sedimentary rock formations. Seasonal flash floods generate extreme hydraulic forces, rapidly transforming dry wadis into destructive torrents. Yet this hostile hydrology was engineered into a controlled, sustainable water distribution network. The Sikh functions as a Prakritic conduit, channeling floodwaters through a confined geological corridor. Its height and narrow cross-section amplify flow velocity, increasing erosion and hydraulic pressure. Solar penetration is limited, creating microclimatic gradients affecting evaporation and moisture retention. The sandstone surface reveals tool marks indicating systematic anthropogenic modification for hydraulic purposes. This canyon operates as both threat and opportunity within Petra's integrated environmental design. Carved channels positioned along canyon walls demonstrate intentional elevation above peak flood levels. These conduits maintain controlled gradients, enabling gravity-fed water conveyance without mechanical assistance. Rising placement minimizes sediment intrusion and protects the system from debris-laden floodwaters. Nabataean masons utilized precision tools to carve uniform hydraulic sections into the rocks. Impact points and chisel patterns reveal advanced stoneworking techniques optimized for durability and flow efficiency. Access to elevated channels required vertical navigation, indicating planned maintenance pathways and inspection routes. Topographic alignment ensured optimal inclination angle to achieve steady laminar flow conditions. The system integrates seamlessly into natural geology, reducing structural stress and material requirements. Conceptual mapping reveals an interconnected network that operates according to the principles of balanced hydraulic distribution. This is not an isolated construction, but a unified hydraulic infrastructure embedded within the canyon itself. Extended channel networks reveal deliberate spatial planning aligned with canyon morphology and hydraulic efficiency principles. Elevated conduits demonstrate precise vertical zoning to separate potable water from high-energy flood flow. Diversion points are strategically angled to redistribute flow while minimizing turbulence and structural erosion. The entire system reflects advanced understanding of topography-driven water routing and hydraulic pressure. This interconnected network operates as a gravity-fed distribution system across multiple elevation gradients. Atmospheric instability triggers sudden precipitation events, rapidly increasing watershed runoff volume. Initial rainfall saturates sandstone surfaces, reducing infiltration and accelerating surface runoff rates. Accumulated water converges into wadis, forming high-velocity flow within confined canyon geometries. Flash floods exhibit turbulent flow regimes, carrying sediments and debris with significant kinetic energy. Within the Sikh, hydraulic pressure intensifies due to the limited cross-sectional area. Impact forces against canyon walls generate erosion patterns and structural wear over repeated events. Floodwater depth increases rapidly, overwhelming natural drainage and eliminating safe passage. Aerial perspective reveals the complete transformation from a dry corridor to an active fluvial system. Uncontrolled flow would compromise any unprotected urban infrastructure within this environment. Hydraulic chaos introduces multi-directional pressure forces, destabilizing unsupported rock surfaces. Transported debris amplifies destructive potential, acting as abrasive agents within the flow. Peak discharge moments produce maximum shear stress along canyon boundaries. Complete inundation transforms the Seek into a temporary river system with no exit strategy. Post-flood conditions reveal erosion marks and sediment deposition across surfaces. This cyclical threat demanded engineered intervention to ensure urban survival and continuity. Stone retention dams were constructed to intercept flood flow and dissipate kinetic energy upstream. These structures exhibit tight masonry joints, reducing seepage while maintaining structural stability under pressure. Incoming flow is split at the dam face, redistributing hydraulic loads across multiple exit channels. Diversion channels redirect excess discharge away from critical urban zones inside Petra. Branching pathways create a distributed flow network, minimizing peak discharge concentration. Internal dam composition reveals layered stone placement, enhancing load distribution and resistance to shear stress. Water is funneled into carved tunnels, initiating controlled subsurface flow transmission. Tunnel interiors maintain consistent cross-sections to stabilize velocity and reduce turbulence. Extended rock-cut tunnels act as pressure regulators within the hydraulic system. Outlet points reintroduce water into surface channels at controlled discharge rates. Open canals exhibit smooth stone surfaces, minimizing friction losses along the flow path. Sequential channels guide water across varying elevations through stepped gradient design.
Channel geometry is optimized to maintain laminar flow under moderate discharge conditions.
Subtle slope variations regulate velocity without inducing erosion or overflow. Curvilinear marches reduce flow energy by distributing directional change gradually. Multi-level channel systems allow vertical distribution of water across different urban elevations. Macro-scale layout demonstrates integrated flood control and supply infrastructure. Flow to divide ensures equitable distribution while preventing hydraulic overload in any segment.
Minimal leakage indicates high construction precision and material compatibility with sandstone.
The system operates as a cohesive hydraulic machine, balancing control, storage, and distribution. Terracotta pipes are embedded within sandstone walls, forming sealed conduits for pressurized water transmission. Pipe joints are carefully fitted to minimize leakage and maintain consistent internal hydraulic continuity. Flow inside these ceramic pipes remains stable, protected from contamination and external evaporation losses. Sectional analysis reveals a closed distribution system integrated inside the rock mass itself.
This network of pipelines extends across Petra, linking sources to storage nodes.
Large rock-cut reservoirs act as primary storage units, buffering fluctuations in water supply. Internal reservoir surfaces reduce seepage while maintaining structural integrity under hydrostatic pressure. These chambers are dimensioned to store seasonal runoff, ensuring year-round availability. Multiple inflows feed each reservoir, increasing redundancy and system reliability. Distributed storage creates a decentralized network resilient to localized failure.
Filtration basins utilize layered aggregates to remove sediments and improve water quality.
Gravity-driven filtration slows flow velocity, allowing particulate matter to settle naturally. Outwater exhibits higher clarity, suitable for domestic and agricultural use. Sequential treatment stages reflect an early understanding of water purification engineering. The integrated system combines collection, storage, filtration, and distribution in a unified cycle. With reliable water supply, vegetation begins to establish within an otherwise arid ecosystem. Irrigation channels distribute water efficiently across cultivated zones within the city. Localized microclimates emerge, reducing ambient temperature and improving habitability. Water availability supports daily life, enabling permanent settlement and urban growth. Public water features reflect surplus capacity and confidence in system stability. Petra evolves into a fully functional oasis, sustained by a precisely engineered hydraulic ecosystem. Green landscapes contrast sharply with the surrounding desert, demonstrating controlled environmental transformation.
Open channels and concealed conduits operate simultaneously, delivering water across urban and agricultural zones.
Urban life here depends entirely on a continuous, regulated water supply from engineered sources. Water abundance allows architectural expansion beyond survival, enabling spatial and social complexity. Trade caravans are drawn to this stable resource hub, reinforcing Petra's regional economic dominance. Market activity thrives, supported by predictable water availability and infrastructure reliability. City-scale planning reflects a city designed around hydraulic efficiency and resource distribution.
Solar light interacting with flowing water enhances both environmental quality and visual urban identity.
From above, Petra appears as a self-sustaining oasis embedded within a hostile geological context. Modern researchers analyze the system, uncovering advanced principles of ancient hydraulic engineering. Laser scanning and digital modeling reveal the accuracy of carved channels and gradients. Comparative analysis shows parallels with contemporary water management and sustainable design strategies. Digital reconstructions map the full extent of the Nabataean hydraulic network. Simulation models confirm efficient flow distribution with minimal energy loss across the system. Preserved channels demonstrate long-term durability under thousands of cycles of environmental stress. At sunset, Petra reveals the harmony between architecture, geology, and water engineering. Every carved surface reflects intentional design, merging structural function with environmental adaptation. As the camera withdraws, the vast desert emphasizes the improbability of this engineered oasis. Petra stands as a timeless case study in sustainable design, where engineering mastery reshaped nature itself.